Good morning, dear students. In the last class, we were discussed about the basics of signals and systems. So in that, we come across what is signals, what is system, and some of the classifications of signals and systems. Elementary continuous time signals, that is the basic signals. Operation on signals and systems. Some different approaches are there that you have studied in the previous class. So in this class, we will study about elementary discrete time signals. Already we have studied elementary continuous time signals. So this in contrary discrete time signals are present in signals and systems. So elementary discrete time signals, as I already told in the previous video, there is a difference between continuous time signals and discrete time signals. That means continuous time you can define signals at any instant of time, but in case of discrete time you cannot define signal at particular instant. So you can see this. In this case, we cannot define the signal in between 1 and 2, or 0 and 1, or minus 1 and 0, and minus 2 and minus 1. That is what the difference is. But in case of continuous time signal, you can define the signals at any instant of time. So best example is a sine wave. So these are the elementary signals. The very first one is exponential signal, next is sinusoidal signal, third is exponentially damped sinusoidal signal, fourth is unit step sequence, fifth is unit impulse sequence, and sixth is unit ramp sequence. These signals are also there in continuous time signals. Here it is discrete, there you are studied about continuous time signal. So the very first one is exponential signal, that is discrete dt means discrete time exponential signals. So it is given by x of n is equal to c into alpha to the power of n. Either c is a constant, alpha is variable, and n is also variable. So whenever alpha is greater than 1, whenever the alpha is greater than 1, the waveform gradually increases. So in case of continuous time signal, a exponential wave is there, that is gradually increasing. But here it is a discrete time sample. You can also trace like this. This is your gradually increasing exponential signal. When alpha is greater than 1, signal will be gradually increasing, that is exponential signal will be gradually increasing. If alpha is less than 1, that is 0 less than alpha less than 1, then it decreases. It decreases like this, it is going to decrease. When this condition exists, minus 1 less than alpha less than 0, then this will be somewhat, this is similar to a sinusoidal signal, similar to that of sinusoidal signal. And if alpha less than minus 1, then it is a one-sided gradually increasing signal. You can have a look at this. Here at positive axis gradually increasing, at negative axis gradually increasing. This is what the discrete time exponential signal is. Next is sinusoidal signal, that is discrete time sinusoidal signals. In case of continuous time signal also the equation is same, but there you are using omega naught. Here it is discrete time sample omega naught, that is x of n is equal to a cos omega naught n plus phi, where a is the maximum value of x of n, a is the maximum value of x of n, x naught is an angular frequency, phi is a phase angle in radians, and n is dimensionless. And one more thing, keep in mind that discrete time signals are not periodic. These discrete time signals are not periodic, but continuous time signals are periodic. For periodicity, you cannot check the discrete time signals. So that is what discrete time sinusoidal signal is. Next is discrete time exponential damped sinusoidal signal. So for that, this is the equation: x of n is equal to c into alpha to the power of n sine omega n plus phi. So when x of n decreases as n increases. That means here the x of n depends upon the value of n. So when you go on increasing the value for n, your x of n will going to decrease. You just remember this equation while solving the problem, it will be helpful. So next is discrete time unit step sequence. So in general, unit step sequence. So with respect to discrete time, this is an example. You can have a look at this. At 0, amplitude of the signal is 1. Till infinity it will be 1 only. So look at this condition. So u of n is equal to 1 when n greater than or equal to 0. You can have a look at this. U of n is equal to 1 when n greater than or equal to 0 means at n is equal to 0, that is n is equal to 0, amplitude is 1. When n is greater than 0, then also it is 1. N is greater than 1 means it is 1, 2, 3, 4. Then also it is 1. Till infinity it will be 1 only. So when n is less than 0, so before this time scale, that is at -1, there is no signal. Is existing. That's why it is 0. So this is what the example for unit step sequence. So in case of continuous time signal, the signal will look like this. This is example. You can refer the previous video for continuous time signal. This will be one. There you are mentioning it in u of t. Here it is u of n, because it's a discrete time sample. That's why we are using u of n. So if it is a continuous time signal, then we are going to represent it by u of t. Next, discrete time unit sample sequence. This is similar to that of continuous time signals. There also the sample will be at 0 and its amplitude will be 1, and representation is also similar, almost similar. In that case, you are going to use an arrow. Here it is a dot to indicate that is it in a discrete time form. That's why they are giving it in a dot. You can have a look at this. So when n is equal to 0, its amplitude is 1. You can check this. At 0, its amplitude is 1. So when n is not equal to 0, when n is not equal to 0, then it will be 1. So that means if it is present at 1, then it is 0. If it is present at 2, then also it will be 0. So in left side case, in the left half of S plane, if it is present, then also it will be 0. That is at -1, that is in left half of S plane, it will be 0. At -2, then also it will be 0. If it is present left half of S plane or right half of the S plane, then the unit impulse sequence will be 0. It has to present at, so if you want to get the value for impulse sequence, then it has to be present at 0. So next is unit ramp sequence. So this is unit ramp sequence. This is an example for unit ramp sequence. When r of n is equal to n, when n is greater than or equal to 0. Look at this. When n is greater than or equal to 0, it is n. That means the signal is existing. It shows, the n shows the existence of signal. When n is greater than or equal to 0, it shows the existence of the signal. You can draw like this. It shows the existence of signal. So So when n less than 0, there is no existence of signal, that's why it is 0. So this is unit ramp sequence in case of or with respect to discrete time samples. So in the last class I have forgotten one more signal that belongs to unit that belongs to continuous time signal, that is a ramp signal with respect to continuous time sequences or continuous time signal. This is the best example. Unit ramp function r of t is equal to, you can have a look at this, is 0. This is with respect to continuous time signal, r of t is equal to t when t greater than or equal to 0, and 0 when it is r of t is equal to 0 when t less than 0. You can have a look at this. When t greater than or equal to 0, the signal is gradually increasing. This is a ramp. This is a ramp. This is a ramp. R of t is equal to t, t greater than or equal to 0. That means it shows an existence. The signal is existing at when t greater than or equal to 0. So when t less than 0, there is no signal. That's why it is 0. So you remember all these signals. These are the very important signals. So in order to solve the problems, these signals are required, and also the operations which I have explained in the last class. Okay, thank you.